Recording in progress.
Okay, so let's start with the next session, first session of today, and first talk is given by Shengwen Li, and it's relaxation, recurrence, and isolated finite many-body systems. Over to you, Shengwen.
Well, thanks for the introduction. I'm Shengwen Li. So today I'm going to talk about some of our study of the symbolization and relaxation process in isolated systems. Well, I want to start from an old problem, which is called the problem of irreversibility. So consider we have an open system. Usually, we consider we have a heat bath, which is in the thermal equilibrium, which is very vast, very huge. And we have a small open system. Finally, no matter what the initial state is, finally, it always relaxes to the canonical thermal state, which has the same temperature as the bath. And for most physical observers, we could see some relaxation behavior. After some time, it becomes a steady state. Well, and we also have the Clausius inequality during this process. This irreversible entropy always keeps increasing. Well, this is a problem for open systems, no matter quantum or classical. But if we have an isolated system, especially for quantum system, we know the quantum system, it follows the unitary evolution. So somehow I would expect the observers, they should always change in with time. However, if we calculate the entropy of this whole system, it always gives us a constant. So this looks contradictory with our intuition that the entropy should always increasing. Well, actually, this is not the problem for only quantum systems and also exist for classical systems. If we have many-body classical system, the whole for ensemble state follows the Liouville equation. This is just a classic. Well, this von Neumann equation is just the quantum counterpart of this Liouville equation. So, if we calculate the total entropy by using the Gibbs entropy of the four ensemble state, you always find that according to the Liouville theorem, this entropy is also always keeping a constant. Well, notice that no matter how many particle numbers and what kind of interaction, or whether it is integrable system, you always have this total entropy is equal to the should always be a constant, even for classical system. Well, this is the paradox of the irreversibility. A typical example is the Loschmidt paradox. When if we have a moment, we can reverse all the direction of the particles. You could say this diffusion process is reversed from the full system, go back to this part. So why for macroscopic thermodynamical systems, we have irreversibility? So why we have relaxation? So how can we, especially how can we have, for a few body system, we have deterministic evolution, but for many body system, we have irreversible dynamics. Well, in the Nobel Prize lecture, Prigogine mentioned that the laws of classical and quantum dynamics seems that it's preventing us from constructing something like the entropy we want. And the reversibility can only be introduced by introducing some kind of a cost graining, and he don't like that, and I also don't like that either. Well, here we want to think about something different. Well, for example, this is classical gas, which contains many particles, and this is a full ensemble state. But actually, we should notice that for many macroscopic thermodynamics, thermodynamical observables like the pressure and the temperature, when we calculate these macroscopic thermodynamical observables, we only need the single particle state, but we don't need the full ensemble state. For example, as we know, the temperature is just the average kinetic energy of the particles. And when you calculate it, you only need the single particle distribution. And this is the same for the pressure, which is defined by the average force applied on a surface in a unit time. So you could notice that all of here, you only need the local single body distribution, but you don't need the full ensemble state. So inspired by this idea, here we consider a finite spin chain system. Well, for simplicity, here we consider a quantum XX model. For example, this is on-site energy, and the interchange energy with the nearest neighbors. This is the quantum XX model. This model can be exactly solved by the Jordan-Wigner Fourier transform. And you can find out that here we consider this side, we treat it as the system, and all the others as the bus. This one, initially it is in the excited state, and all the others are at the ground state. And you can obtain the full evolution of all the sides. And it turns out this function, we have an analytical result. You could prove that in the thermodynamical limit, this decay function, it becomes a Bessel function. And but at a finite size, you find that if we look only at this single side, this decay function, it gives you this blue line. It's quite interesting that you could see at this stage, it gives you a quite ordinary, regular oscillation decay, and at a certain time, it suddenly changed. And then it seems that the dynamics looks random. Well, of course, this is deterministic, but of course, comparing with this part, certainly it looks random. All right, this is three important features. If we further consider, we change the system size n, we have larger and larger n, you could find that at this stage, this oscillatory decay, they are the same. And this is a recurrence. And you could see with the increase of the size, the recurrence is postponed later and later. And at this area, it is becoming more and more random. Actually, except this recurrence, this line, actually it means this part. So it is also some kind of a recurrence. You could see some different lines. So here we call them as hierarchy recurrence. And every time after a recurrence, the dynamics looks more and more random. And more interesting, you could find that this recurrence time is just the system size times an integer number, and later we will show why this is the reason this result happens. So if we have n approaches infinity, you could say, well, I know this recurrence would be postponed to infinity. In that case, actually no recurrence happens, and we could only see this relaxation process. Well, in this sense, we could say if we only focus on this local observable, you could see why we have relaxation process. Well, to understand this structure, here we show the probability evolution of all these different sites, and you could see a propagation pattern. Initially, the system probability start from here, and then it propagate to the two different sides. And here we could see such kinds of picture. Initially, it's concentrated here, and then it propagate in these two ways. At this time, these two propagations, they meet each other at the end, at the other side of this chain. After that, they would continue propagate. This gray one would go to this should go this way, and this blue wave should go this way. So at this point, they meet each other again, and these two waves, they are superposed together. That's why here and here, right at this point, we observe a recurrence happens. And of course, after this recurrence, this wave would continue to propagate and regather again and again. Every time they meet each other, you could see recurrence. That's why we have seen the hierarchy recurrence, and the recurrence time is just the system size times integer number. And of course, this propagation speed is characterized by the coupling strings. Well, in this sense, we explained the reason for these recurrences, and actually we have analytical expansion for this decay function. You could slightly see you could find that can be expanded as a series of Bessel functions. For example, this phi 0 is J0 and this Jn. For example, if we have n equal to 100, this is J0, and this is J100 and 200. And so at this stage, this J100 actually doesn't take effect, and only after this recurrence time it starts to oscillate. And this is also for J200. That's why the later the time is, we have more oscillations classed together, and they would appear more and more random. So this is the here we explained why the recurrence happens, but here we still want to see some quantity to describe the entropy, because especially the irreversibility behavior, if we consider the total entropy, it never changes with time. If we consider the entropy of each single site, they always changing with time, from time to time. we can't see any irreversibility behavior. In comparison, here we consider another different quantity, which is called the total correlation. Well, this is just the summation of all the entropy of each single site minus the total entropy. For example, you have only two bodies. This is just the mutual information which characterize the amount of correlation between these two bodies. And this total correlation is just a straightforward generalization for many-body systems. So in this system, if we calculate this total correlation, we would find that, well, this is the total correlation. And this is a single, the entropy of a single site. You could see that, well, at this stage, it shows, well, roughly almost an irreversible increase. But of course, here, it seems that some kind of a recurrence happens. And as this part, it looks a little more random. And here we consider we have different sizes. You could see if you have larger size, this increase in profile becomes more and more smooth. And we could here we could say, well, it's increasing monotonically. I mean, before this recurrence appear. Well, since it is increasing monotonically, we would ask, what is the final point of this increasing behavior? What is the possible maximum of this total correlation? So to have the possible maximum, we calculate the maximum of this total correlation, but we need to consider we have two constraints. First, for this model, you could find that the total excitation number is conserved. And of course, the probability is conserved. Under these two constraints, you can calculate this total correlation by using the Lagrangian multipliers. And you would find that when all the sides are equal to each other, you have this maximum. And this is just the blue lines here. And so you could see this theoretical maximum is just quite close to the dynamical evolution result. And here we show the relative error. I mean, this part, this small part. You could see with increase of the site number, this error is smaller and smaller. It's becoming smaller and smaller. Of course, we expect in the thermodynamic limit, they would just equal to each other. So in this sense, it seems that this system is relaxing towards some kind of equilibrium state. We call it a pseudo equilibrium state, and this is just calculated by obtained from here through the correlation maximization process. Well, we also consider a quantum Ising model. This model also can be exactly solved as before. And but here we have a strong coupling and weak coupling regime for this coupling strength and self energy. You could see actually they have very similar pattern, although the time is different. And first we have oscillatory decay, which is regarded as a relaxation process, and then we have recurrences, also the hierarchy recurrences. Actually, you can prove that this quantum Ising model in the weak coupling case by applying the rotating wave approximation, it could return to the quantum XX model. And also you could see this is scaling behavior, and this propagation understanding still applies.
So
and
just,
this is
just a few minutes left, really.
Yeah, I see. And almost 3 pages.
Good.
And this is the total correlation. And this is the strong coupling case. Well, I think I don't have too much time. You could see this correlation maximization process still applies. Although there are strong oscillations here, but here we could apply the coarse graining. And if we apply coarse graining on this oscillating curve, you could have a smooth envelope, and you could also see this relative error still applies. Oh, I think I don't have too much time. Well, you could find that still this applies for the negative temperature case. So in this case, actually, this thermal entropy doesn't apply well, but this you could find that this correlation maximization also applies, and it directly gives you the evolution result. So in this sense, this correlation entropy, it plays the role of entropy. Well, I think I don't have too much time. Anyway, you can find that obviously this total correlation, it directly gives you the Boltzmann-H theorem. It is equivalent. And this is the case of open systems. After some approximations, you can prove that this total correlation also gives you the standard entropy production rate. Well, thanks. I'm sorry.
Thank you. Just a little bit over, but thank you very much. Maybe if there's one question that somebody wants to ask, please go ahead. Just connect. No questions? I thought it was very interesting. I mean, the spin boson model, which comes at the end there, that's something I've studied a lot, and we know well how it relaxes with exponential decay. And for a finite system, you get those kinds of recurrences that you were talking about earlier on. Actually, a few years ago, I had a master's student who never really finished the project working on that chain model, but with the atom at the end of the chain. You have it in the middle. And it would be interesting to know if this exact result you have with the Bessel functions would work as well for the atom at the end. I suspect so. Do you have any quick view on that? So taking your XX model with the atom at the end of the chain.
You mean the Bessel function expansion, right?
Yeah, would that still work for that system? Just quickly.
I'm not sure, but for this model, this expansion is just for this quantum XX model actually. For the Ising model, I didn't obtain this similar result, but from of course I think this propagating picture still applies.
Yeah, it still applies. If you have the atom at the end of the chain, then you have one like wave packet going off to the end and then bouncing back.
Yeah.
I'm going to cause the session to run late, and I'm chairing this. So let's thank Shengwen again if we are doing so.
Yeah, thanks.
Online that, and move to the next talk. Thank you, Shengwen, which is Igor Ryabtsev, I think.
Mm-hmm. Thank you.
3-photon laser excitation of mesoscopic ensembles and single rubidium Rydberg atoms for quantum information.
Yeah, thank you.
Thank you. So Igor, go ahead.
Do you see my screen?
Yes, but not in full screen view, just like presenting.
Now?
That's better. Yeah, that's good.
Yeah, okay, thank you. First of all, I would like to thank Olga for inviting me to this nice conference. And I will be talking about 3-photon laser excitation of rubidium Rydberg atoms. And I remember that Rydberg atoms are atoms in highly excited states. The energy are described by this Rydberg formula, where n is the principal quantum number and delta is quantum defect. The energy levels in rubidium atoms are shown here. The ground state is 5s, and Rydberg states are the states near the ionization threshold. And we can excite Rydberg states by laser radiation. For example, this can be 1-photon excitation, but this requires ultraviolet photon, which is not convenient. Most often used is 2-photon excitation of S and D states, but in our experiments, we are using 3-photon excitation of the NP states in rubidium atoms. So Rydberg atoms are distinguished by large orbit radius of the valence electron, which scales n square, long radiative lifetimes like n cube, and huge polarizabilities of Rydberg state, very sensitive to electric field, and the polarizability grows as n to the 7. And if we apply a strong enough electric field, we can finally ionize the atom as soon as the electric field reaches this critical value that strongly depends on the principal quantum number. And this provides a way to detect single Rydberg atoms. This so-called selective field ionization detector. So we have the atoms between two electric field plates. We excite the atoms to Rydberg states by short laser pulse. Then we have some time for interaction of atoms between each other or with external radiation. And then a ramp of the electric field is applied. So the Rydberg atoms are ionized. And depending on the state of the Rydberg atom, this ionization occurs at different times. And then single ions or electrons can be detected by a particle detector. In our experiment, we use a channel-clone detector, and we have found that in the histogram of the output pulses, we have several peaks corresponding to different number of the detected atoms. Therefore, in our experiment, after each laser pulse, we measure in which state were the atoms and what was the number of detected Rydberg atoms. So we can deal with mesoscopic ensembles of Rydberg atoms. And there are many motivations to study Rydberg atoms, and most important are neutral atom quantum computing and electric field sensors. So how can we use the Rydberg atoms in quantum computation? Suppose we have a quantum register based on single rubidium atoms in optical dipole probes. In order to make perform 2-qubit gates, we need to switch the interaction between atoms on and off. But ground state atoms don't interact between each other with the distances of a few micrometers. Therefore, it was proposed to excite the atoms for a short time to highly excited Rydberg states. And as the dipole moment grows as n squared, then the energy of resonant dipole interaction grows as n to the 4. And in this way, it is possible to implement 2-qubit gates. So we can estimate that if we take the distance of 5 micrometers and n equal 100, then the interaction energy will be as large as 100 megagates, which is enough for fast quantum gates. So, and why it is interesting to excite Rydberg states using 3-photon excitation? This is because we can implement Doppler and recoil-free laser excitation, and this can be arranged in this way. So we just take the C radiations and shine the atoms by this radiation in such a way, in such geometry, so that the sum of the k vectors of these 3 laser beams is equal to 0. And in this case, they automatically suppress the residual Doppler effect and recoil effect. And this allows, in principle, to improve the fidelity of Rydberg quantum gates and spectroscopic resolution. So in this paper, our quite old paper, we compared theoretically the excitation spectra for 1 photon excitation, 2 photon, 3 photon excitation for the atoms with different temperatures. It is seen that for 3 photon excitation in our specific geometry, even at room temperature, we can observe a very narrow resonance. In theory, the 3 photon laser excitation can be modeled using a 4-level model like this. Here, the parameters are these are 2 intermediate states. These corresponding Rabi frequencies of single photon transitions. But if you take a large detuning from the intermediate states, the system eventually converts to 2-atom system with some global omega Rabi frequency, which is given by 3 photon Rabi frequency. Here we have the Rabi frequencies at each step and the tunings of the first step and the third step. And we have found in this paper that it is possible to calculate analytically the line width of such a 2-level system, and so in principle we can make the analytical calculation. However, most of all, in most cases, we are using the numerical solutions. So this is our experimental setup. It was a rubidium magneto-optical trap equipped with selective field ionization detector, and we excited the atoms to Rydberg states and then detected them. The atom had a temperature of about 100 microkelvins. And these are one of our results. Here we implemented 3 photon excitation with large detuning from intermediate state, like okay, with detuning about 100 megahertz, and this is our observation. We observed 3 photons.
Practically,
some problem.
Or someone should switch off the
let's. I think I propose to continue with the next.
Chair doesn't have any control.
And maybe
do you have a mic control?
Is it Jiwen Zhang?
Yes, this is
Jiwen Zhang, can you mute, please?
No, it's not me. It's not me.
Is it Shengwen Li? Radionchev, maybe. Now it's gone. Thank you. Sorry about that. Go ahead.
So this is a peak of coherent 3 photon excitation when the 3 photons are absorbed simultaneously. We also observe another peak which corresponds to 3-step excitation. Then in this case, the intermediate states are excited at the wings of the Lorentz profiles. And this peak is weak and it is incoherent because the photons can be absorbed in different time. But these 3 photon excitation should be coherent with Rabi oscillations, and it is a rather narrow resonance. And if we apply a weak electric field, we can observe, for example, the Stark effect in shift and splitting of this particular 37p3 half state. Okay. In our other experiments, we investigated the line shape of the 3 photon resonance, for example, for the 37p3 half state, depending on the interaction time. For large interaction time, like 2 microseconds, the width is about 1 megahertz. When we decrease the interaction time, we can observe the Fourier broadening and the appearance of the signatures of Rabi oscillations at the wings of this 3 photon resonance. Then we implemented the 3 photon excitation for high Rydberg states. For example, we excited up to 120 p3 half state, and the resonance was quite narrow, like 3 megahertz, and this allows us to speak about implementing such highly excited atoms in quantum information. As I said before, we have a single atom resolutions, and we can analyze the multi-atom signals that we detect, how they depend on the number of ground state atoms. So we can introduce the mean number of atoms excited per laser pulse from an ensemble of N0 ground state atoms. Here it is, and here this is the probability to excite a single atom. And then the probability to excite n atoms from an ensemble of N0 atoms is given by normal distribution. If you take into account the finite detection efficiency T, which in our experiment is about 60%, then this is a modified probability distribution. This is a probability to excite more than n atoms and detect n atoms, taking into account the detector efficiency. So the full measured signal S, which represents the mean number of atoms detected per laser pulse, is given as a sum of multi-atom signals, and making inverse conversion, we can show that these multi-atom signals can be expressed via the measured full signal and number of atoms this way. And this is what we have observed in our experiment. In this particular experiment, we compared the multi-atom spectra for the 39p state, 81p state, and 110p state. And this column represents the full signal S, which corresponds to the mean number of Rydberg atoms detected per laser pulse. And these are S1, S2, and up to S5. This spectra corresponds to the probability to excite and detect exact number of atoms. In this case, we detect only one atom, in this case 2, 3, and so on. And what we see in this experiment that for 81 and 110 p states, the probability to excite 4 and 5 atoms and even 3 atoms is suppressed. And this is the signature of that we observe a partial dipole blockade effect. Dipole blockade corresponds to the case that when we excite a single atom, it blocks the excitation of other Rydberg atoms due to the energy shifts of the collective states. But in this experiment, we observed only partial dipole. Finally, we investigated the dynamics of laser excitation for the multi-atom signals. Here again, we have a total signal S, and these are single multi-atom spectra from 1 atom to 5 atoms. What is interesting here, we have a deep and single atom excitation spectra because this is just a statistical effect, not interactions. It is due to the fact that the probability to excite more than 1 atom is high. Therefore, we observe this statistical view. And this column represents the dynamics of measured signals. This is for full signal, this is for single atom, 2 atoms, and for 5 atoms. So we see the dynamics are quite different. First, we excite 1 atom, then more probably 2 atoms, 3, and so on. And I forgot to say that here the green lines are theoretical calculations. So with our simple theory, we can model the signals for any number of atoms. Then we have decreased the number of atoms to N0 equal to 5 and increased the Rabi frequencies and observed some signatures of Rabi-like population dynamics. And actually, what we want to have in this experiment is to achieve high contrast Rabi oscillations at Rydberg excitation. We are now working on quantum information processing. Recently we had launched a new experimental setup for implementing quantum gates with single rubidium atoms in an array of optical dipole traps. And here are the arrays of optical dipole traps, and the atoms are trapped there, and we observe the luminescence. Here we have 2 traps, 4 traps, 3 traps, and a 3x3 array. And these arrays are formed using a special light modulator. This is a phase masks of the SLM for creating such kind of traps. So in our first experiments, we trapped was just 2 neighboring ground state atoms, we could change the distance between them, and the lifetime of two atoms in two dipole traps was about 10 seconds. Recently, in this year, we have implemented also single atom loading of three traps and 4 traps. Then we implemented the experiments on microwave transitions in two neighboring ground state atoms in neighboring optical dipole traps with individual undressing. These are the microwave Rabi oscillations. We can excite Rabi oscillation in one trap and suppress it in another trap, and vice versa. And actually, observation of such oscillations correspond to implementation of single qubit gates with fidelity about 97%. And finally, what we did just a month ago, we implemented the 3-photon excitation of a single rubidium-97 atom in a single optical dipole trap using this setup and this excitation scheme. What we observed that if we do the experiment in a working magneto-optical trap, we observe two peaks. One peak is a coherent 3-photon excitation, another peak is incoherent 3-step excitation. This is because here we use just pulling radiation at the first excitation step. But when we trap a single atom to optical dipole trap, we observe a rather narrow resonance with a width of about 1 megahertz, and the contrast was about 50%. Here we don't use the selective field ionization, we just use optical detections of single Rydberg excitation. To the best of our knowledge, this was the first implementation of 3-photon excitation of a single rubidium atom. And finally, what I want to say that 3-photon excitation can be also is also important for Rydberg sensors of radio frequency or microwave fields like this one created by a group of York Wright. Typically, in such sensors, they are using a 2-photon excitation by red radiation and blue radiation in optical glass cell with rubidium vapors, and the two laser beams are counter-propagating, and without microwave fields, they observe a single resonance of electromagnetically reduced transparency. When they apply additionally resonant microwave radiation between two neighboring Rydberg states, this single peak splits in two peaks, and this splitting is directly defined by Rabi frequency of microwave transition. What is important here that at 2-photon excitation, the typical width is about 5 or 10 megahertz. Therefore, this limits the sensitivity of such kind of detector. But recently, the group of James Shafer from Canada has implemented 3-photon excitation with cesium atoms, and this is a comparison of the spectra without microwave radiation. This is for 3-photon excitation, this one is for 2-photon excitation. So they obtained the 10-fold narrowing of the resonance. In fact, the resonance had only 200 kilohertz width, therefore they have significantly improved the sensitivity of this Rydberg sensor. And they could detect extremely small microwave fields. So, and here I come to my summary. I don't know, should I read or not? I just show like that. Thank you for your attention.
Okay, thank you very much. Thank you. Do we have any questions? Yes? No?
Yeah, can I ask a question? It's Irina Novikova.
Go ahead.
Hi, thank you very much. Very, very, very interesting talk and very impressive results. I have as maybe a little more practical question. When it comes to the 3-photon excitation, there are obviously many passes to take. So how did you decide on which 3 lasers are you using, and are there any other options? Because as you will hear from my talk next, we work with vapors, and we are very interested in using this technique to localize the atoms or potentially to narrow the resonance.
Okay. If you are working with rubidium, we just had some lasers like 7 180. This is for first excitation step for 5P. And the next step, it can be two different states. We have chosen this particular state, 6S, because this wavelength corresponds to telecommunication lasers. And our first experiments were made with a distributed feedback lasers, just for telecom. And the third step is titanium sapphire. In principle, now it is possible to replace it with semiconductor diode lasers with amplifier. So this was our choice, but actually in rubidium, Mikhail Lupin uses a different scheme, but 2-photon excitation. But for 3-photon excitation, I don't remember exactly. Probably someone also used it. I don't remember through which state. But of course, you can use, for example, on the first step, not D2 line, but instead you can use D1 line, and the wavelengths will be different.
Thanks.
Yeah.
And Olga, you have a question, I think.
Thank you.
Yeah, thank you so much, Igor. Very exciting results. But I'm afraid I missed maybe one point as I was distracted for a minute. And so that I understand that 3-photon excitation is specifically important when you are dealing with ensemble of atoms to avoid Doppler broadening and recoil. But if you are dealing just with single atom in optical lattice, is it still, what are the advantages?
Yes, this is the same because when you have a single atom in an optical dipole trap, it is not immobile. It has some residual motion. And this motion is also accompanied by Doppler broadening, residual Doppler broadening. In this particular scheme, you completely compensate for the Doppler broadening. And in addition, if you use this scheme, you don't hit the atom when you excite it to Rydberg state, because atom absorbs the momentum. And if you use, for example, 2-photon excitation, it starts to move faster. This particular state, it remains on its plane. It does not obtain additional moment.
But how in this case can operate with 2-photon excitation in the optical lattices like Misha Lukin?
Yes, in 2-photon excitation schemes, they are using counter-propagating
to compensate, I see.
Yes, and you may see that here we did the calculation for 2-photon excitation, also for two counter-propagating beams like this one and this blue radiation. And it is better than single photon.
So it's about the same in this case, right? Either you have to counter-propagating or you satisfy phase matching as you do, right?
If you take co-propagating beams, these 2-photon resonances will be much wider.
Of course, but I mean, as compared to what they are doing, counter-propagating, it's about the same, or there is still some
Yes,
advantage?
they partly compensate for the Doppler effect, but because the wavelengths are different for second step and first step, you cannot compensate it for completely.
I see. Thank you.
Thank you.
Okay. And if there are no other questions, apart from one I've got, which I'll ask whilst we change, Irina, can you put your presentation up?
Thank you.
Igor, can I just ask one last question? From the point of view of, if you can let your presentation go, from the point of view of quantum information processing, how efficient is the state of potential qubits, to detect that in this system?
Sorry, can you repeat?
So how efficient is the process of detecting the final qubit state?
Okay. So in our
Just
new
a quick number
setup, we are using optical detection. Optical means that we measure the fluorescence of the atoms in the ground state under illuminating it by resonant red radiation. So we measure the fluorescence signals, and we are using a sensitive camera, scientific CMOS camera that is able to detect emission from a single atom.
It's efficient then, yes. The longer you fluoresce it.
To distinguish between two ground sublevels or hyperfine sublevels, we first make the so-called pushing out atom in one state, or we don't do this for another state.
Okay,
This
thank you very much. Igor,
yeah.
I need to move to the next talk. Sorry,
Yeah.
I would love to talk longer about it, but let's all thank Igor again if we have audio on. We move now to Irina's talk on Rydberg EIT resonances. Irina, over to you.
Hello, thank you very much for being here. Thank you much, Olga, to inviting me. That's one of my favorite conferences, and I really hope that in the future we will be able to be in the same location together, not just on the internet. Nevertheless, let me continue the topic of Rydberg atoms, and thank you, Igor, very much for the wonderful introduction. I will be talking about the different ways we proposed to potentially create the narrow resonances. Unlike Igor, I work with the vapor cells, and that's why making narrow EIT Rydberg resonances is really important for us. So, of course, this work has been done by not just me, but many other people. So this was a collaboration between Draper Lab and William and Mary group here. You can see everybody's. And essentially in this talk, I will be discussing on how we propose to use the Ramsey approach to the Rydberg EIT resonances. And at least theoretically, it seems like it should be working, but unfortunately, in experiments, we have not been really able to observe it. So I'll talk about that. So as I said, Igor already gave the excellent introduction on the Rydberg atoms. We are particularly interested in Rydberg atoms for metrology applications. And because Rydberg atoms contain the highly excited electron, their dipole moments is huge, and therefore they're very sensitive to external electric fields. How we can measure that, again, using the more traditional approach is using the EIT resonances, where we have two optical fields to excite the atoms into the Rydberg states. In this case, because Rydberg states have a long lifetime, we can create the coherence between the ground and excited Rydberg states. And in this case, this long lifetime coherence gives us narrow resonances. And if we now apply RF field, or electric field, the Rydberg resonances will be, again, either shifted or splitted. And by detecting this changes in the Rydberg state energy, we will be able to detect electric field. There has been a lot of progress done in this field, just like one of the review articles, but there is a lot of interest and a lot of different applications for electrometry, radio detection, spectrometers, and so on. And I think people are still really exploring where this Rydberg measurements can help. However, as Igor pointed out, if we don't want to work with the cold atoms, we run into a problem because atoms in the vapor cells are moving. That means that we have to deal with the Doppler shift. And even though we can partially compensate for the Doppler shift by, for example, having the atoms propagating in opposite direction, because the wavelength is so different, we cannot really make the resonances narrow. As it was mentioned, there are ways to use, for example, 3-photon excitations, but then, especially for the warm atoms, it not always work as good as we want, especially if they need to have fields propagating in slightly different angles that reduces their volume. So we would like to try something different. In particular, in atomic systems, we know that if we have resonances which potentially have a very long T2 times, but for some reason we cannot achieve it, one of the interesting approaches to use is to use the Ramsey approach. So, for example, for the CPT or EIT atomic clocks, this has led to significant successes. In particular, the problem which are resolved in these systems is the problem of power broadening. Because in order to have a good signal to noise, it's always good to have a strong signal. However, in all EIT systems, if we have, for example, strong optical system, that then produces the broadening of the resonance and therefore kills the sensitivity. Raman-Ramsey resonance helps with that. The idea, of course, is that the atoms are prepared in the coherent superposition during the first stage. Then the fields are both turned off, so there is no interactions happening. And then they're turned off after a fairly long time. And in this case, what comes out on the second part is essentially the interference of the evolving coherence with the optical fields. And in this case, it's possible to observe the much narrower fringes, because in this case now, if there is any phase change during the evolution in the dark time, that essentially will determine the sensitivity of the fringe. So this way, even if we have a strong optical field on the detection stage, we have a good suppression of, let's say, short noise, but we're not affected by the power broadening that strongly. As I said, this approach has worked wonders for the CPT atomic clocks, and is widely used right now. So we would like to try to see if we can use it for the Rydbergs. So this is our model for the cold atoms. And of course, in this case, it's a great idea to use the Ramsey fringes, because the lifetime of the Rydberg state is much, much longer than the time of the, let's say, excited state, intermediate state. And we can get a very nice sharp fringes. However, again, we're not dealing with the cold atoms, we're dealing with the warm atoms. So what can go wrong then? So, of course, motion of atoms introduces a bunch of problems. So first of all, if we just thinking of the traditional Raman-Ramsey approach, the motion of atoms in kind of transverse direction away from the laser beams will limit of how long the atoms can stay around. So in this case, it limits evolution in the dark time, because if the atoms are leaving the laser beam, they're not going to come back. However, which is kind of much more serious problem, is the Doppler effect for once, because again, now if the atoms are moving, only a small fraction of them will see the optical fields, and moreover, only they will have a different two-photon detuning, so they kind of evolve differently. But another effect will be, and this, of course, this is the same thing as we see for the CW EIT. However, the other one, which is more specific for the Ramsey interrogation, if the atoms are moving along the beam, the relative phase of the optical fields along the beam is going to change as well. So that means that if at the end of the preparation, the atom was in one location, but then during the dark time, it's actually moved along the beam, when the fields are on, that means that the atom is going to see the different relative phase of the optical field, which of course will be different from the dark state it was prepared. So this is kind of how it looks in the picture. So if this is the Ramsey fringes for the three types of atoms, so yellow here is the motionless atoms. And at the moment, we're considering only the longitudinal motion. We see that the atoms are moving with a relatively small speed, plus or minus 3 meters per second. If we take into account their Doppler shift, we see that the pictures are shifting from each other. If we take into account this relative phase shift, fringes are also start to get dephased. Luckily, what happens is that if both of the effects have in place, some of them, they actually compensate for each other partially. So the good news is that even if we put everything together, the final fringe kind of survives. So we'll see some of the signals there. So this is how it looks kind of in our modeling. In this case, we consider three-level system with kind of realistic atomic parameters. And what is happening in this case, in the bottom here, I show the simulated data for different two-photon detunings. And you can see that the first, we prepare the atoms and then we turn on optical field. They stay off for about 500 nanoseconds. That's our evolution dark time. And then when we turn field back on, depending on their two-photon detuning, we see a kind of strong variation of the transmission before the atoms are kind of pumped back to their corresponding dark states, and then we go to the CW kind of levels. Again, optimistically, if we are now integrate for, like, say, first 100 nanoseconds of this recovery time, and then plot it as a function of the two-photon detuning, it appears that the fringes still still survive. They're not as strong as they would be for the purely cold atoms, but some of the fringes survive. So this is kind of the optimistic. Here I should assume, although, that we did not consider the atom escape in the laser beam. So this is very optimistic picture. However, even in this case, we will have to take it into account, and that's going to severely limit of what dark times are possible, for example. So another system implementation we considered was inspired by our previous work with the Lambda system EIT, and it's actually what kind of started this project. In this case, we considered two laser beams. Each of them has like its EIT channel. And what we discovered rather accidentally in our experiments is that in this case, the relative phase of the optical field between the channels actually play the roles. And the atoms who just ballistically flew through one beam into another had enough coherence to show some differential signal. And we have analyzed it and showed that in principle, we can use this transient signal for some of the measurements, and they are not as quite good sensitivity. So the idea was, can we implement the same idea, but now for the Rydberg atoms? So in this case, it may potentially resolve some of the problems. So for example, it can be purely CW case, because now we create two independent optical channels, but there is no need to turn the optical fields on and off. And also in this case, we at least partially escape the problem of atoms escaping the laser beam, because now the dark time will be controlled by how far the beams from each other, and that can be relatively long, even though the atomic beam size may be small. So the time atoms spent inside the laser beam is fairly short. So the one thing, of course, we have to consider compared to our previous model, it's obviously look very similar, that the atoms are prepared in a steady state, and then they cross the laser beam. That's how dark time, where they in between the beams, and then they enter the second beam. That's where detection is happening. Of course, because the atoms are thermal, now the time they spend in the dark are going to be different. So that means that even in ideal case, if in this case we assume no longitudinal motion, only transverse, in this case we discover that the fringes period is going to be different depending on velocities. But even in this case, this central fringe is still going to survive, and kind of its width will be determined by ultimately fairly slow atoms. So to wrap up this part with a lot of kind of numerical modeling and checks, it appears that in principle this should work. So even if we take into account the mismatch of the Doppler effect and the phase velocity inside the laser beam, if we just model the atoms which has both longitudinal and transverse velocities, it seems that the central fringe should appear in this measurement. It's very small. It's much smaller than the original EIT contrast, but it should survive. And what is even more promising is that if we apply this RF field, the fringe should split just the way it's done for the regular EIT atoms. Again, this is probably the most optimistic picture. Now, how we can estimate if it's better, because here obviously the system is not ideal, because the fringe itself, its amplitude is very small compared to the overall EIT, even though it can in principle be narrow. So as a figure of merit, we kind of take a numerical derivative of our signal.
We lost.
I don't hear.
No, she's frozen. Irina, I don't know if you can hear me, but your presentation is paused and your video. So hopefully she's aware there's a problem and will try to reconnect or something. It completely cut out suddenly.
Yeah.
Olga, you might try to call her. my phone.
Uh,
Maybe she does not know that it's not broken.
I don't have your phone number.
No.
Yura, do you have it? Yuri? I don't
No,
see him.
no.
You don't
I-
have?
No, I don't have it.
Maybe she will reconnect because I think she's left the meeting.
Yeah.
Yeah, well, my experience is if you talking when it was, this COVID, and you doing lecture and you cut off, then sometimes Zoom is reconnecting. That's good, but sometimes it doesn't, and then only students send me email saying that you talking, but you're actually frozen.
Yeah. It's something more likely to happen if you have a low bandwidth connection.
Yeah. So yeah, we should send the email.
Okay. Well, we can wait a minute or two for her to sort out the problem. In principle, looking at the schedule, the next talk should already have started because we're running late. And I see Warwick's connecting for the talk after that. So what we could do, as she doesn't appear to be reconnecting, we could move to the next talk and then Warwick's and then return to Irina if she connects again at the end. What do you think, Olga? Is that sensible?
It's what I'm writing to her right now.
Okay, so we'll come back to at the very end for her to finish the talk. And we'll move now to the next talk, which is William Shannon.
Yes.
So
do you see my screen?
I do.
Yes.
It's there.
Can you hear me?
Good.
Yes. Okay. Very good.
Everything's good. So I think you should just set off on your
ahead
talk.
and start.
15 minutes. Yep.
Yes. So hello, I am William Shannon, and this is my talk on two-mode squeezing and entanglement, atomic boson sampling that I did with my graduate advisor, Professor Vitaly Kokorovsky at the Institute for Quantum Science and Engineering at Texas A&M University. So the idea here is that we have this new way to do boson sampling as described in some of our previous work, whereas rather than using a linear optical interferometer with external sources of squeezed photons that sent through some sort of unitary matrix U system described by some unitary matrix U to be measured in some final state to do this boson sampling problem, we have this idea of making use of an equilibrium interacting BEC gas in a trap to do atomic boson sampling on the excited state fluctuations of such a system. And so it's perhaps less explored so far than this optical system, but we're hoping to justify some further use of this idea. So the model that we'll be using for the present discussion is a box trap with periodic boundary conditions, as this helps simplify the analysis by creating a uniform condensate wave function. The field operators for excited atoms are described just as normal with this annihilation operator. But perhaps most importantly is to note here that the Hamiltonian for such a system is quadratic, has these off-diagonal terms, which leads to us having to make use of the Bogoliubov transformation to diagonalize the Hamiltonian, as is sort of a custom for this. It's a very normal thing to do. But what is perhaps abnormal and interesting in this case is making use of something called this Bloch-Messier reduction to take this Bogoliubov transformation and break it down into three different components, this R sub W, R sub R, and R sub V, which makes use of these two unitary matrices, V star and W star, along with the diagonal matrix of M single mode squeezing parameters, this matrix here with these squeezing parameters involved. And we do this because each of the components in this Bloch-Messier reduction has a clear physical meaning describing a certain process that's occurring in this BEC gas. This R sub V is describing interference, and so some sort of entanglement that's occurring corresponding to this unitary rotation V star from the basis of the bare atom excited states that we have pre-selected for sampling to the atom numbers into the basis of eigensqueeze modes. Then this R sub R is the squeezing component, which is describing the presence of these terms beyond the resonant wave approximation in the Hamiltonian, creating and annihilating pairs of atoms from the condensate. And then this R sub W finally describes an Perhaps somebody has this mic open again.
Somebody needs to mute the...
It sounds like it's similar to what was happening last time, so I'm not sure. Oh, it's gone now. Okay. So continuing, this R sub W describes an interference due to this unitary mixing W star of the eigensqueeze two-component excitations that were just formed in the second step into the eigenenergy quasi-particles. And so you can see here this sort of figure showing the process that we have just described above. This observational bare atom basis becomes this eigensqueeze modes, which then goes to these eigensqueeze two-component excitations, and then the eigenenergy quasi-particles. And this is important because these eigensqueeze modes are uniquely determined by the interaction Hamiltonian, and their eigenvectors constitute the multimode, the eigenvectors of the multimode squeezing matrix, and their eigenvalues are the single mode squeezing parameters. And so this is sort of just as important to the discussion as the eigenenergies of the quasi-particles would be. So this is a sort of unique deconstruction that is done here. And then one other thing to cover before we get too deep into the weeds is that we will be making use of something called a covariance matrix to do this joint probability distribution, which is defined here. Its entries are given by the quantum statistical average of these column and row block vectors of atom creation and annihilation operators. We have these anomalous and normal correlators that we'll be using going forward, where the anomalous correlator is this average for these two annihilation operators, and the normal correlator is the annihilation and creation operator. These subscripts represent the different modes, but for all the future slides, we will just be doing the self-correlators, and so these subscripts will be dropped. And so the perhaps idea for the first choice of these eigensqueeze modes would be the standing plane waves, which is the simplest choice because it completely eliminates the interference and thus the first and third steps of the Bloch-Messier reduction, leaving only squeezing. And so this yields just very simple sampling statistics that perform as expected. We have here for all of these situations, the normal correlator is fixed at 8 equals 8, while the anomalous correlator is set in blue at 0, then 8 in green, square root 70 in yellow, and then it reaches its maximum value, which is the square root of eta times 1 plus eta here in red. And you can see that it begins as sort of a thermal distribution before, as we increase the value of this anomalous correlator, we start to see the situation become more and more depleting these odd numbered modes until eventually when we reach the maximum value of alpha, we reach a fully squeezed vacuum state with zero thermal occupation and a complete depletion of these odd numbered modes, which can start to be seen even as we approach this maximum value here in yellow. Now, the more interesting choice, what we will be spending some more time on, is this choice of two counterpropagating traveling plane waves for our choice of eigensqueeze modes, as here we will include now interference and squeezing, which leads to a much more non-trivial joint probability distribution of atom numbers in the two modes. And we start by constructing this covariance matrix, which you can see here with these normal correlators along the main diagonal, the anomalous correlators in the off diagonal, where here NK is this average number of quasi-particles, and then these RK are our squeezing parameters. And then from here, what we need to do is discuss something called a covariance-related matrix, which is constructed from the covariance matrix using this formula here and this permutation matrix P. This is important to do because it is what is used in this Hafnian-Master theorem to construct the probability distribution. The Hafnian-Master theorem makes use of the matrix Hafnian, which is a matrix operation that is a generalization of the matrix permanent, which you may not have heard of, but you probably have heard of the matrix determinant, which is its sort of cousin. And the matrix determinant, we take these products of entries and alternate adding and subtracting them to a sum, whereas in the matrix permanent, we strictly add all of these values together. And whilst the matrix permanent sounds simpler, it's actually more complex to compute than the matrix determinant. The determinant is has many polynomial time algorithms, whereas the matrix permanent is number p complete to compute in general. And so is the matrix Hafnian. And so this is sort of the core of the complexity of this problem and where this number p difficulty comes from. And so in this specific case, we have this construction for the covariance related matrix where these zeros are just blocks of entirely zero entries. These J matrices are blocks of entirely ones. And then these alpha primes and eta primes are the covariance related matrix equivalents to the anomalous and normal correlators from the covariance matrix, which will be specifically defined on the next slide. And so you can see here, this matrix is half zeros. And so we can reduce this Hafnian to its specific case, the matrix permanent, by doing some rearranging and to reach this position here, where you can see we just have these two diagonal square blocks of different sizes of eta prime values, and then these two off diagonal rectangular blocks of alpha primes. And with this, we can do the combinatorics to just calculate the permanent because it's just these very simple constant blocks. And we reach this final result here for the Hafnian through the permanent of this function using the hypergeometric function here. And then we also have now defined this eta prime and alpha prime in terms of the normal and anomalous correlators. And so from here, we have everything we need to plot these sampling statistics. And so you can see, again, we have for all of these, the normal correlator fixed at eta equals 8. Well, here in the top left, we have the pure thermal distribution at 0 anomalous correlator. And then as the anomalous correlator increases to 8, square root 70, and then again to its maximum value of square root eta times 1 plus eta, we begin to see a diagonalization of the statistics, which can sort of begin to barely be seen here. It's sort of more strongly pronounced here. And then eventually we have this purely entangled state, which is completely diagonalized the statistics here. And so we can look at this result in the two extreme cases to sort of verify the maps are working as intended. We start first with alpha, the anomalous correlator being set to 0, which leads to alpha prime being 0. And then the other case will be the maximization of the anomalous correlator, which leads to eta prime being 0. And so in the first case, the complex permanent that we had previously is simplified into the product of two simple permanents of constant matrices, because in the case of the value of alpha prime being 0, we only have these two diagonal eta prime blocks, which are both square. And so we can just take the permanents of these two matrices separately, as seen here. And then the permanence of this matrix is simple. It's just all the same value. And so we very quickly reach this product of two thermal distributions. They're completely disentangled. There's absolutely no correlation between these two values. Whereas in the second case, where eta prime is 0, our diagonal entries are the ones that are zeroed out now in this block matrix, and we only have these off-diagonal blocks of alpha primes. And the leading term of the asymptotics here, you can see, includes this permanent and will only be evaluated to a non-zero value when these two off-diagonal blocks are square. And so that leads to this delta, Dirac delta function here between N1 and N2, and the purely diagonal distribution for the probability. And that means that they're completely entangled, which is exactly, again, as expected. And now this may all seem as if it's just sort of theory, but there's already much technique and some experimental work that is being done to perform the relevant experiments in showing these statistics. I want to first of all point to a group, a Polish group, that has successfully measured the fluctuations on the total number of condensed atoms in the harmonic trap. And while this is not necessarily exactly what we would need to do these sort of statistics, it's still very important, because measuring this total non-condensate occupation and discriminating it from the much more populated condensate that is still very energetically close in a trap with such a large number of atoms, they have 5 times 10 to the 5 atoms, is very impressive and a very important first step towards this sort of work to be done. And perhaps more excitingly, we also have work done by the Clements group in France, whose papers are here, whose figure I have borrowed, as they have specifically measured pairs of atoms in plus minus k momentum modes using these time of flight experiments, and are also capable, using their very strong detectors with single atom resolution, of taking these full counting statistics for an interacting Bose gas. So you can see here in their figure, they have this BEC that they have trapped somewhere. And at some point, they will abruptly release this trapping cloud, allowing the atoms to expand outwards and then fall downwards due to gravity. And then they will land on this array of detectors, and their momentum can be measured due to their distance that they have been able to travel during their time of falling downwards. And so they have been able to do this to have strongly correlated pairs of atoms measured with opposite momenta, which is almost exactly what our statistics are about. And so the idea is that with the full counting statistics, one could perform more complex experiments and hopefully move towards the ultimate goal of showing quantum advantage. And so in conclusion, we explore and illustrate here atomic boson sampling statistics and a simple model for this interacting BEC gas. The strong and important components here of this are the effects of squeezing and entanglement, which are described in the different blocks of the Bloch-Messier matrix. And we also are trying to say that experimental realization of this is not far of the possibility. Lots of work is being done. And we hope that the sort of ultimate goal is that this atomic boson sampling could potentially be used for demonstration of quantum advantage or supremacy of this quantum systems over classical computation. And so I would like to thank the Hermann F. Heap and Millie Bell Heap Texas A&M University Endowed Fund for supporting my graduate studies in quantum optics, because without them, none of this research would have been possible on my end. And I would like to thank you all for listening and for providing me a space to speak. And then questions.
Thank you very much. Thank you very much, William, and nicely kept to time. Do we have some questions then? Any questions at all? It was technical in places, but you nicely explained some of the terms you were using and gave a bit of context there. So
Thank
if
you.
there are no additional questions, then I think we'll move to the next talk. But let's thank William again for his talk. And just to remind you that the plan is then that we'll go next to Warwick Bowen's talk, and then we'll return to Irina's interrupted talk by Warwick after that. So that's our plan. So over to you, Warwick. Good to see you.
Good to see you too. And good to see everyone. Thank you very much, Olga, and everyone else for putting this together again. It's a great conference to be involved in, even if I can't be there in person. I hope you can all hear me okay. I guess you can, because Barry, you don't look like you're panicking. Good. Today, I'm going to tell you about some work in my lab which is aimed at achieving quantum control of mechanical resonators at room temperature. This work was funded by the Australian Centre for Engineered Quantum Systems and in part by the US Air Force. The main people who really did the work, and I should acknowledge, are Chao Meng and Sharuj Kadimi, who are two very gifted PhD students, along with a bunch of postdocs and other students. And I'm going to take a little diversion at the start because I had a paper that came out a couple of days ago, which I think is really quite nice. And so I'll tell you a bit about that as well. And that was work of Amy van der Hel's PhD. Okay, so let's start. So the stuff I'm going to tell you about is in the area of quantum optomechanics, which many of you will know of, but some of you won't. So the basic idea is that you have a mechanical resonator. So this is this mirror on a spring, and its vibrations interact with light in a cavity via radiation pressure. So if you imagine light hitting the mirror, it's going to make it move, and that motion will then change the length of the cavity, which will change the cavity resonance frequencies, which will change how light gets into the cavity, how much light gets into the cavity, which will then change the radiation pressure, which changes the motion of the mirror. And you can see this sort of dynamical back action where the mirror motion affects the light intensity, which affects the mirror motion. And that dynamical back action is very powerful for doing all sorts of interesting things, from conditioning non-classical states of mechanical resonators to test macroscopic quantum mechanics. Does quantum mechanics work the same at large scales as small scales? To a range of quantum technological applications, from quantum memories to interfaces, communication systems, and components of quantum computers. So one of the applications that's been identified as particularly important for optomechanical systems is in interfaces, to interface between traveling quantum states, which will typically be on light, and solid state quantum states, quantum systems where processing happens. So I'm showing you here an image of the Google quantum computer. You can see there are many, many electrical lines in this computer, and that's only going to get worse. And then, and so the thought is that optics could be used both within the computer to link things up with high bandwidth and to connect computers into a network. But then you need to solve this problem of how you transfer terahertz optical fields into gigahertz or megahertz solid state characteristic frequencies of solid state. And optomechanics is the leading, or maybe one of two leading platforms that are thought to help us solve this problem, because both microwave fields and optical fields interact via radiation pressure with a mechanical resonator, so it can mediate interactions between the two. And here's a very nice example, a recent paper from Konrad Lenden's lab, where he takes a superconducting qubit, prepares a non-classical state of a microwave field with it, and then injects that microwave field into a microwave resonator, which interacts with the mechanical system, which is also interacting with light, and ends up, and the net effect is that this non-classical state ends up popping out onto the optical field. So you can transfer this non-classical state from the superconducting qubit into light. But this experiment, and every experiment to date in optomechanical state transfer, has required that you reach what's called the resolved sideband regime This is the regime where the mechanical frequency is large compared to the optical decay rate. So that means you have a high frequency mechanical oscillator and a high Q optical cavity. And that's prohibitive for many sorts of optical cavities and many mechanical resonators you might want to use in an interface. So a few years ago, so today I want to tell you about a new paper that came out from my lab this week that resolves this problem, that allows it's the first proposal for a continuous optical to mechanical quantum state transfer that works outside of the resolved sideband regime, that will work for low frequency mechanical oscillators and low Q optical cavities. And it's based on a simple observation that a common experiment that people do with optomechanics is feedback cooling. So you have light, it comes into your cavity, it interacts with the mechanical resonator. The phase of the light picks up information about the mechanical position, this Q. The phase is the Y. You measure the phase, and then if you apply an appropriate filter and then use the photocurrent to apply a force on the mechanical resonator, you can cool it. You can apply a force that's proportional to velocity, and that damps the energy in the mechanical resonator and cools it to close to, and ultimately can cool it. And people have shown that this is possible to very close to its quantum ground state. But the question is, if you've cooled it to very close to its quantum ground state, you've essentially transferred a vacuum state onto the mechanical oscillator. But what is that vacuum state? Did it come from light? Did it come from some other part of the mechanical spectrum? What is it? And our speculation was that somehow what you're actually doing is a state transfer from light onto the mechanics. And so we did a bunch of calculations, which I won't bore you with, but you can find in this paper. And the conclusion of those calculations is that indeed feedback cooling is an optomechanical state transfer. It in fact picks one sideband off the optical field and transfers that onto the mechanics. And it's nice, you can, if you were to populate that sideband with an interesting state, such as a cat state or a fox state, then with sufficient optomechanical interaction, you can perfectly transfer that state. So here I'm showing Wigner functions. The blue is negative regions of the Wigner function, which is like a negative probability and is characteristic of a quantum feature of a state. So we're really excited about this because it opens the door to do state transfers and for optomechanical systems to be interfaces in quantum technologies without requiring high Q and without requiring high frequency mechanics. And what's interesting is to get into this regime where you can do a quantum transfer, you need exactly the same criteria as in feedback cooling, which is very experimentally achievable with existing technology. So these sorts of experiments should be possible with the technology we have today. Okay, so that was my sort of aside on the stuff that we've just got published. And what I promised to talk about was preparing non-classical states of mechanical oscillator via measurement. So this was about, I can take it, if I've got a non-classical state on light, I can transfer it onto the mechanics. But can I just use a direct measurement to prepare a non-classical state? And can I do that with a room temperature oscillator that is integrated on a chip? Because if I could do this, then I could start to build quantum optomechanical technologies that would be compatible with your phone or with other sorts of portable devices, which would be very, very cool if you could. And to try to answer this question, we went back to this exact same problem I just told you about, but instead of applying a force on the mechanical resonator, we asked, what is the best estimate of position and momentum of the mechanical oscillator you can achieve just from continuously measuring the photocurrent that interacts with the optomechanical system? This is a very old question that's been looked at in many, many, many papers, but generally people take what's called the rotating wave approximation. And it turns out that removes some really interesting physics that we think provides a powerful way to produce non-classical states. So that's what I'll tell you about for the rest of the talk. So one question you could ask is, how do I determine what the optimum filter to choose here is to estimate position or to estimate momentum? And it turns out that for this sort of interaction, and for causal estimation, the commutation relations work out just right so that you can use classical estimation theory from engineering to optimally estimate and provably optimally estimate the position of momentum. And those that your choices are to use Wiener filtering or Kalman filtering. And we chose Wiener in our experiments that I'll show you soon and in our theory. But I'll give you an example of an application. So Wiener filtering is really very widely used in engineering. One area that it's used in science is in analyzing the cosmic background radiation. So this is a raw trace of the cosmic background radiation without filtering, and you can see there's a bunch of noise and probably some distortion, I'm not sure, around the perimeter of the image. When you apply a Wiener filter, you clear all that noise up and you get an accurate and minimum noise estimation of the signal. So you can apply the same thing in estimation of position and momentum of a mechanical oscillator. I don't have time to go through the details, so I sort of skipped them. But the net effect is that if you look at the Wigner function of the oscillator, and this is position and momentum, then if it starts out thermal, so very broad, with the measurement you're able to localize the oscillator to some spot and ultimately to a spot of width given by the 0-point motion of the oscillator. And so the common understanding, when you take the rotating wave approximation, the conclusion is that once you get to a spot the size of the 0-point motion, as you increase the optomechanical interaction strength further, you really achieve nothing. It doesn't change the state. You just end up with a vacuum state on your mechanical oscillator, or a coherent state actually, because it's displaced, and it's not a non-classical state. And this is sort of represented here on the standard diagram that people use in quantum optomechanics. The horizontal axis is the thermal occupancy of the mechanical resonator. The vertical axis is the optomechanical cooperativity, which tells you something about the interaction strength. And so if I was to start at, say, 10 to the 5 phonons and increase the cooperativity, you'd see I get this gradual cooling until I hit the 0-point motion and then a plateau once I have cooperativity above the thermal occupancy. So it turns out if you do the maths for optimal estimation without taking the rotating wave approximation, instead of this understanding, you get quite a different understanding, which I'm showing you here. So in the sort of lower left part of this figure, you reproduce what was understood previously, but in the upper right, you see very different. You see two new phases of dynamics. So, well, okay, so I should say lower right and upper right. So in the lower right, you see the symmetry between position and momentum start to break. You can learn more about the position and the momentum of the oscillator. And then in the upper right, you start to see squeezing being exhibited. So this is precision on the position of the mechanical resonator that's better than the 0-point motion. And this is a non-classical state of mechanical motion. So it turns out that without that rotating wave approximation, you can produce non-classical states just with a continuous measurement. And one of the things that I think is exceptionally interesting about this is that as you increase the thermal occupancy, so if I was to start at a cooperativity of 10 to the 4 or something, if I increase the thermal occupancy, initially my estimate gets worse, but then eventually it starts to get better again. And if I go up to high enough thermal occupancies, then I can reach the quantum regime, and I can reach that regime at far lower cooperativities than even ground state cooling would be possible for ground state cooling. So you can achieve a quantum non-classical state, and you can do that with low cooperativities. I should say the way you should understand this plot is that we're fixing temperature at room temperature, and in order to increase the occupancy, we're decreasing the frequency of the mechanical resonator. So really, you should think about this being decreasing the mechanical resonator's frequency, and because and then you can understand why you see this effect. It's because the the environment interacts with the mechanical resonator through its momentum. You get thermal kicks of the momentum of the mechanical resonator, but we're measuring position in an optomechanical system, and the position, and so in order for the noise that's entering the momentum to get to position, the oscillator has to rotate, it has to oscillate a bit. And as you decrease the resonance frequency, you slow that transfer of noise into position down, and you essentially freeze out the environment, which is what allows you to achieve these non-classical states with lower cooperativities than even ground state calling. Hopefully that was clear. So I've done an experiment to attempt to achieve room temperature quantum squeezing. We haven't quite got there yet. So I let the cat out of the bag, but this is the experiment. We have what's called a double disc resonator, showing you a photograph of one here. It's made out of silica. It's basically 2 discs of silica, and light is trapped around the perimeter of each disc. And this forms an optomechanical system because the disc has mechanical modes, and a key mode is the flapping mode, where the top disc moves up when the bottom disc moves down. That mode is very strongly coupled to light because the light is mainly occupying the region in between the 2 discs. So you get an extremely strong optomechanical coupling to that particular mode. So our idea is we have our device. It's in a vacuum chamber just to increase its mechanical quality factor. Light comes in, interacts, picks up a phase shift, and we detect that phase shift using a local oscillator as a reference phase. Taking the difference gives us an estimate of the position of the mechanical oscillator and also of the momentum. This is if I take that photocurrent that I measure and I take the Fourier transform, what I see is a series of peaks, these spikes. The spikes that are shaded in red are mechanical resonance frequencies. A specific mechanical resonance is this big one, is that flapping mode I told you about. The small one here is the symmetric mode. So similar mode, but both discs are moving in the same direction. And then there's 3 other modes up here, which are higher order modes. The gray peaks are nonlinear mixing peaks between the modes, and they don't actually matter for the experiment. They don't play an important role. So if we look at these first 2 modes, then it turns out one interesting piece of physics we didn't expect is that they don't show the usual viscous damping you expect from mechanics. So normally mechanical systems are damped proportionate to their velocity, and that gives you a flat response at low frequencies. What we see instead is a noise that grows at low frequencies. And that's a characteristic of what's called structural damping. Structural damping has received a bit of attention recently in the quantum community because it shifts the mechanical noise around, it shifts it to lower frequencies. And that means that that it actually enables you to do interesting experiments if you want to work with high frequencies within this spectrum, if you want to work out here somewhere. So we were a bit worried because for us, it turns out it's this low frequency response that's important. And now we've got increased noise. We thought that would make the performance of the devices worse. But after doing some analysis, what we found was actually exactly the opposite. So here I'm showing you again that plot of the thermal occupancy versus optomechanical cooperativity. And the white curve here is the transition between to quantum squeezing for viscous damping. And when you switch on the structural damping, you find that in fact you can achieve quantum squeezing at lower cooperativities. So it actually makes the system better, which was a surprise and a nice one for us. So we then set about doing some estimation experiments. State preparation experiments. So here we're doing 2 experiments. In one case, we're defining this first mode as our signal mode, and the second mode is noise, just degrading the performance. The Wiener filter that optimally estimates that first mode is then this blue filter shown here. In the second case, we're considering a collective mode of motion of both modes. So we're treating both modes as signal, and then the Wiener filter is nice and flat because there's signal here, and you want to keep both. Whereas if this is noise, you want to really suppress that because it's got a large amplitude. And then when we do estimation, we see things like this. On the left of this plot is just the raw photocurrent from our device, and you can see it's oscillating. That's the mechanical oscillation, but it's got a lot of noise. When you apply the filter, you find that the noise gets smoothed out nicely. We can check how well the filter is working by taking a second estimate of, in this case, the position of the mechanical oscillator, but with future data rather than past data. And we can compare those two estimates to get an idea of how accurate we are, and the uncertainty, the difference is shown in the light blue. Yeah. Okay. So then if I calculate that, if I measure the position of momentum and I plot them on a phasor diagram, I get plots sort of like these ones. So on the left is the pink data points. There's millions of data points in there that you may not be able to see. Are estimates of position of momentum at a whole bunch of different times. And you can see they form a nice Gaussian distribution, which is what you expect for thermal noise. When we turn the estimation on, we ask now, what is the uncertainty in the estimate? Then you can see I can really reduce the noise down. I can condition the state to a lower entropy state. Here the green is when I consider the two-mode case, consider both modes as signal, and the blue is when I just consider the first mode as signal. In both cases, you can see that we're reaching this first new regime we'd predicted, where the symmetry between position and momentum is broken. Here, the uncertainty in position is reduced compared to the uncertainty in momentum. And using two modes, you reduce the uncertainty a bit more than with one mode. So that's nice. We're still very far away from achieving quantum squeezing, unfortunately. And the reason for that, it turns out, is that there are many high frequency modes that I'm not showing you here. And those modes contribute noise, which it turns out degrades the performance of the conditioning. So you can ask, well, how can you do better? How could you achieve the quantum regime? And our conclusions are you can do one of two things. You can either employ a single very low frequency mechanical resonator, so design a mechanical system to ensure that there's one low frequency mode and all the other modes are at much higher frequencies. One example of that is the N mirrors of gravitational wave interferometer. We're currently in discussions with LIGO about potentially using their interferometers. And the second is it turns out you can use a large array if you can have many very similar resonators at the same sort of frequency, then that can also be used to achieve quantum squeezing. So with that,
Warwick, I think you're into negative time, but come to the right slide. Great. Thanks.
Sorry, I wasn't sure where I was in terms of time. So anyway, I'm finished now. Apologies if that was more time than it should have been.
That's fine. That's my fault for letting you go on, but very interesting talk. Thank you very much. So a reminder that we're returning to Irina's talk. We have time for a couple of questions on Warwick's talk, but we should be mindful of time because I think this same channel gets used for the plenary session on the hour and people will start joining that soon. So Vitaly, you have a question for Warwick.
Thank you for the very interesting results. It's very impressive. May I ask you just two questions? First, we're talking about non-rotating wave approximation terms. This is in the interaction between optical and mechanical mode, right? Mm-hmm. Great. So then, did you specify what is the eigensqueeze mode in this system?
What do you mean when you say the eigensqueeze mode?
This is the mode which diagonalizes the multi-squeezing matrix of the system, because you have non-array terms like in the Bogoliubov transformation. You have squeezing induced due to this non-rotation wave approximation terms. And because of that, you have some modes in the coupled oscillations of optical and mechanical system, which exactly corresponds to the single mode squeezing.
Yeah, I think I know what you mean. In this sort of experiment, because you've got a discrete set of eigenmodes, so we've got a mechanical system has a sparse spectrum of eigenmodes. It's fairly easy to determine what the squeezed eigenmode is, and you don't need to do a Bogoliubov transformation. Don't need to look at Bogoliubov physics, I don't think. In the simple case, in the ideal limit, you just have one mechanical resonance and one optical resonance, and then the interaction can be used to squeeze the single mechanical resonance. There isn't a collection of mechanical mode in the ideal limit. There isn't a collection of mechanical modes that you've got to understand what collective mode amongst them is the squeezed one. In practice, we do have multiple modes, and so there is some sort of optimal mode that's squeezed, and we get that out of the Wiener filter actually. And I haven't thought about it in terms of Bogoliubov physics, but maybe we should.
Okay, thank you very much. Is there any other quick question? I'm tempted to ask questions, but we're so short of time. Maybe I'll send you an email, Warwick.
Yeah,
and
please.
We do it that way. Thank you very much again, Warwick, for the talk.
Sorry for going over.
Let's move to Irina then to conclude the talk. And as I said, bear in mind, Irina, that the plenary session begins here.
Yes, I will try to be as quick as possible. I'm so sorry. It's like one brief blimp of electricity and long time for internet to come back. So let me share my screen. Where is okay? Sorry.
Just to finish it off, really.
Yes, I will be extremely brief. No, not this one, sorry. Now, of course, I'm kind of panicking. Okay, so I'm not sure where exactly I disappeared, but the main conclusion was that in order to get the narrow resonances, the optimal configuration seems to be if we have two spatial regions for the Rydberg EIT and let the atoms to move from one region to another. Despite of all the troubles created by the atomic motion, we should have a narrow resonance. And in principle, the sensitivity should be better than for the normal CW-EIT. We tried to see it experimentally, and here we run into some of the problems. So in our lab, we did the time-dependent experiment where we turned the light fields on and off with the AOMs. We definitely see the effect of the population trapped in the Rydberg state. So in this experiment, we prepared atoms in the Rydberg EIT, turn lights off, but turn on only the probe light. And in this case, we clearly see the state preparation. And if we have a longer dark time, we see less and less atoms in the Rydberg state, so missing from the ground state. However, when we tried to see the kind of Ramsey fringes, we really didn't see any specific signature of that. And our Draper colleagues tried to do the same thing with the transverse fields. Again, we see the population transfer from one channel to another, but we don't see the Ramsey fringes. Our current suspicion is that the main reason is the laser line widths. The lasers were not locked to each other, so the phase instabilities between the lasers are certainly going to kill everything. And also, I suspect in our case, the AOM has added some instabilities as well. However, hopefully it's just a technical reason, and it might be possible to see the Ramsey fringes on a Rydberg EIT in the future. And just because I know I don't have a lot of time, I just want to kind of say that why we want to study Rydberg EIT is where we're interested in optical detection of the charged particle. In particular experiment we're doing with electron beam right now. We have observed and mapped the electron beam using polarization rotation, so looking at the magnetic signature of electric beam. In this case, the polarization rotation of the laser beam will reflect the magnetic field, and we can see the laser beam. We are building the experiment where we want to use the same thing with the electric field. At the moment, we do see electric field effect on optical transmission, but unfortunately, that's the charging of our cell. And in the new generation of the cell, we are really hoping to get something and use it again for the detection of the charged particle or potentially for plasmas as well. And I'll just put the conclusion. So theoretically, it looks like it might be possible to achieve the narrow Rydberg-Raman resonance in just a 2-laser configuration in the vapor cells. However, it does put some stringent requirement on the system, on the laser system, which currently we did not have. So thank you so much for letting me finish and sticking around for that. Thank you.
Thank you very much, Irina, and thank you for your talk in a difficult situation and of interruption. Igor, you have a question. Go ahead.
Yes, I have a question regarding your first part of your talk where you discussed the Ramsey fringes at Rydberg excitation.
Yes.
I am thinking about the final goal of this Rydberg sensor is to detect microwave radiation.
Yeah.
Your Ramsey scheme works well without microwave radiation, but how microwave radiation would affect your Ramsey fringes? And my understanding is that it should be considered like a dephasing from microwave radiation, no?
Well, so we did a kind of brief analysis, and I will confess that it's not like a final, so it's like an asterisk that it's like temporary, intermediate results. So we actually ran the modeling where we included the interaction with the RF field with the Rydberg states, basically how it's usually done with the sensors. And what we observed that it's essentially splits the Rydberg states to Atlee-Town splitting, and the fringes are behaving the same way. So we did see the splitting, which is dependent on the strengths of the RF field. So in this case, it truly should increase the sensitivity of the sensor on this narrow Ramsey fringe. However, this wasn't a very thorough analysis. So I mean, we used the same model, but I wouldn't claim that with 100% confidence, I can tell you that it's going to work. So, but kind of quick and dirty test showed that it should work.
Okay, thank you.
Mm-hmm.
Okay, thank you. Is there another question? Yes, Olga, go ahead.
Well, maybe just in 2 words, if you could tell what you expect from the charged particles, how to detect, is it via electric field or what they would change? Mm-hmm.
Yeah, so Olga, thank you so much. So we already have seen the effect of the magnetic field. So if we have electron beam, then magnetic field creates around, and if we shine the laser beam kind of perpendicular to it, you can see here we expect that polarization rotation will be in one direction, kind of above the beam, and the other direction below. And by measuring this rotation protocol, we were able to recreate the density of the electrons. However, magnetic field sensitivity of the atom is not huge, so we can detect electric field, and it's an interesting way of kind of non-contactly measuring the strong electric beam charges. But if you want a better sensitivity, in this case, the electric field should be better. And we expect that as we measure Rydberg shift kind of around the electron beam, we also should see the characteristic feature where it goes kind of up and then down in the center, because if we cross electron beam, that should be no signature or no Rydberg atoms, depending on the strengths of the beam. And in principle, I don't have slide to show it here, but my colleague have shown that in principle, if you do like single atom interferometry, cold atom interferometry, it might be possible even detect the track of individual particles, but that will require quite an effort because it should be interferometric measurement.
Thank you. Well,
sure.
And just to draw your attention that actually we had an interesting talk by Leo Holberg. If you attended it or not, I don't remember. I think not. And he is measuring magnetic field on the level of picotesla using AIT, so it may be of interest for you.
Oh yes, and that's a whole other story of our activity. But actually, for electron, picotesla is not it's not very sensitive. So if we want to go to like individual charged particle, it's really magnetic sensitivity should be unattainable. But yeah, thank you so much. I'll definitely will look at his recording.
Okay. Well, thank you, Irina. If there are no further questions, then I think I will close the session and hand over to the next chair, who I think is not here yet, but that session is due to start in about 6 minutes, I think. So I'm sure.
Thank you so much, Barry. Thank you.
Thank you, Olga.
We meet for plenary session in 6 minutes. Please don't forget. Thank you. See you.
Thank you.